Good evening and welcome to this special lecture. I'm very happy and very pleased that so many of you are able to join us tonight. We are going to do a whole series of experiments with the assistance of a number of people. Before we do any experiments though, we want to make sure that we obey all the safety regulations. To begin with, I will put my eye protection on, my safety goggles, and I want you all to know that we have available, in case we need it, a fire extinguisher. This fire extinguisher will be used only if it's needed. We hope that we don't need it tonight. We are going to have, I hope, a lot of fun, and we are going to, as I said, be doing a series of experiments. And many people are scheduled to help me do these experiments in this special lecture. And I'm going to begin by asking for some help and see if I can get some help now. Here's a series of beakers that we need to use. And here's Bucky. Oh, come on in, Bucky. Come on in, Bucky. Hi, Bucky. We have a lot of special experiments for you, Bucky. I would like to ask you to help out, but you didn't bring your safety goggles with you, so we can't ask you to help out. But can you stay and watch the experiments? Okay, why don't I take you to a seat that I have specially reserved for you over here. All right, here's the seat. Okay. Now, Bucky, we have a special salute for you and for all the Wisconsin fans, and I'm going to ask Fred to go through with the salute for you. So, Fred?
This is a better way to use beakers than any way that most of you know about.
Those beakers contain special chemicals that we're going to be using very shortly, but we'll just set them aside for the moment. To begin with, then, we're going to talk about household chemicals and show some of the properties of household chemicals. As you look around the tabletop here, you see that there are many different samples of household chemicals. Now, you hear me use the word chemicals, and I mean to use that word chemicals because everything that's around us is made up of chemicals. I want each one of you now in the audience to touch a chemical. Touch a chemical. Has anybody touched their nose or touched their cheek or touched that? We're all made up of chemicals, and we need to learn about the properties of chemicals. What I have here then is some household chemicals. We're going to look at their acid-base properties, specifically their pH properties, and I'm going to ask for some help in doing this experiment. I have many friends in the audience, and I want to call on one special friend to begin helping me. That's Alex. Alex, you want to come out and help? Come on out, Alex. Of course, we have a special set of goggles for you, so you can wear the goggles. What I'm going to do, Alex, is you step over there. I'm going to take a few samples of this cabbage. I have some cabbage here. See that? It's red cabbage, right? We're going to try to make some cabbage juice. We'll cut this off like that, and we'll chop it off a little bit, like so. Sounds like the stuff your parents might do at home, right? Right. Try to be careful not to cut our finger. Okay. Then what we'll do is take this cabbage and put it in this blender. So you're watching carefully what I'm doing, right? We'll take this out of the way so everybody can see. We'll take the Vanish and the milk and magnesia out of the way. And put this over there like so. And maybe I put a little too much there. That's about enough there. So what I'll do now is add some water. Add some water to the blender. And what should we do before we start the blender?
Put the top on.
Put the top on, yeah, right, because we don't want anything flying out, right? And then we're ready to push the button. So can you push the button for me? Push. Yeah.
High.
Well, anyone you want. Okay. Now, we'll stop it a little bit and mix it up, right? You've seen your parents do that too, right? You always have to do that with the blender turned off, otherwise it gets hurt. So we'll start again. Okay, we'll stop this now. What we're going to do, in getting this cabbage juice ready, what we're going to do is filter it. So I have a filtering apparatus over here, and we'll pour this out like so. Okay, that's about enough. And this is hooked up to a setup which we call an aspirator. And what I'll do is turn the aspirator on. I'll take those. Lost my microphone. And I will take those two out of the way. And turn the aspirator on. And you can see that the cabbage juice is falling through. And we will collect that cabbage juice and use it as an indicator. Now, we use substances that are called indicators to tell us whether a certain household chemical is acidic or basic. Now, different indicators have different colors. You remember the beakers that Fred used when he played on Wisconsin? Those had acid-base indicators in them. And we're making a special indicator right now. We have enough juice that has come through. So what we'll do is stop. That's about enough. We'll take this off, set it down. See, we have some cabbage juice here. What we'll do is put a little bit of juice in. And you see that big flask with distilled water in it, Alex?
Right.
Can you reach for that? Okay. And just open it up a little bit and fill this beaker with a little bit of water. Well, quite a bit of water. Just pour it, just fill it up with water. Okay, that's good. So what we'll do now is try to measure whether a substance is an acid or a base, depending on the color this indicator solution will turn when we add that substance to the solution. And you see what I have in front of us here is a rack, a test tube rack, that has all it has 1, 2, 3, 4, 5, 6, 7, 8 different solutions in the test tubes. And there's a number on the top of each test tube. That is the pH value that corresponds to this color that we see in the tubes. So what we're going to do first is you grab a test tube like that. Okay? What we're going to do is take some baking soda. I want to take this spatula and put some baking soda in the tube. Can you do that? Okay? Just put a little bit of baking soda in there. And where is the water? Here's the water. Okay, that's good. Then we'll add a little bit of water. Can you reach for a glass rod? Okay, and then just dissolve that. Just stir it up a little bit. Hold it from on top, like where I'm holding it, so everybody can see what you're doing. Yeah, right. See, it's dissolving. So baking soda is soluble in water, right? It's got to dissolve some more. And then what we'll do is add a little bit of indicator to it. And you see the indicator has changed color. Mix it up some more with the rod. Now, the color that we have is going to be close to one of the colors that we have in the rack. So what I want you to do is take this tube and try to compare it to the color closest to it. Which one is it closest to?
7.
Somewhere around there, yeah. So then we know that the pH of baking soda is about 7. All right? So let's try a couple of different other things. You grab another test tube. We'll take some vinegar. All right? So if I put some vinegar in here, what color do you think it'll be? What is it now? It's color, right? It's a colorless liquid. When we add the indicator to it, what do you think will happen?
Red.
It'll be red. That's what you predicted, and that's right. So you tell me now, compare it to the other tubes there. It's about, the pH is about what?
3.
It's between 2 and 4, so it's about 3. So that's acetic acid, right? So let's do one more. Let's do, let's see. Let's try this one. This is household ammonia. What do you think this is going to be? You got the test tube ready?
Green around there.
You think it's going to be green around there? Have you done experiments before?
Yes.
Yeah? Do you like doing experiments?
Yeah.
You weren't too sure there, were you, for a while? Okay, we'll add some indicator, right? And you were right again. It was green, right? So you mix it up a little bit and compare the color, okay? So this is some examples then of household chemicals and how their pH values can be determined using an indicator that we made from cabbage.
Right.
Okay? Thank you, Alex, for helping out. I appreciate it. And all of you give Alex a hand. Okay. Now what I want to do is carry out another experiment. This experiment is to be done in this beaker, this large beaker. It has water in it. In this beaker, I'm going to put in it some baking soda. We'll add some baking soda. And we learned that baking soda dissolves, right? So we'll mix it up, stir it up like so. And we'll get this out of the way so we can do more experiments. Try to shift this over like so. And it's more fun to do experiments if somebody else is helping. So I want to try to see if I can get somebody else to help me. How about Laura? Is Laura here? Laura, you want to come and help? Are you ready? Come on out. You come with me, okay? You want to stand up here? You want to put your safety goggles on? Okay. How old are you, Laura?
5.
You're 5? You like doing experiments? You want to help me do this experiment? Okay, I'll tell you what we're going to do. We're going to take some spaghetti. What I want you to do is to take this spaghetti and break it up into small pieces. Can you do that? All right. Is that too many? All right, let's talk about this many. All right, just break them up. Atta girl. Some more. Okay. Now what I want you to do, Laura, is to put the spaghetti in this beaker. It has in it sodium bicarbonate. Just drop them in there. Can you reach? You see what happens to the spaghetti? It sinks to the bottom of the beaker. Put some more in there. Okay? Are your goggles falling off? All right. Now what we're going to do is add some vinegar to this mixture. What do you think will happen when we add vinegar? You don't know, right? Well, a lot of people don't know. That's why we do experiments, to find out what happens. So let's do an experiment. We add some vinegar. And what do you see happening? Is it fizzing? That tells us that something is happening. We'll take this rod out. This fizzing is carbon dioxide. Carbon dioxide is forming, you see, and it bubbles out, bubbles up actually. Now look what's happening to the spaghetti. What's happening to it? Can you see what's happening to it? You want to tell me? You don't want to tell me? Well, can you see that the bubbles are around the spaghetti and they lift the spaghetti to the top, and then when the bubbles leave the spaghetti, the piece of spaghetti comes down? You can see that, right? That's because the acetic acid that's in the vinegar has reacted with the baking soda and is releasing carbon dioxide. And we can... You're a big hit with the audience tonight. Did you know that? You like it, don't you? Well, we'll watch this for a while, and now you can go back to your seat and watch from over there. So thank you very much for helping, Laura. Okay? Welcome, Santa. Come around, Santa. Come around. Come around.
I have some presents here for you.
Did I hear you say that you have presents for me?
Yes, for
Well,
you in particular.
I made a wish list, and I'm happy to see that you're here, and let's see what you got.
Well, I got some very good ones. I hear you do a lot of experiments with balloons. Is that right?
I do, yes.
Okay, well, here are some
Oh, wow, look at that.
beautiful balloons.
Oh, my goodness. Thank you,
All
thank
right.
you.
Now, you know, I know a lot about you.
You do?
'Cause I keep tabs on everybody.
Uh-oh.
And I hear you're a very sharp fellow. So I brought you this sharp needle.
Oh, thank you. That was on my wish list, too.
Well, that's very good.
Yeah, yeah.
I also hear you often get very thirsty.
That I do, too.
So I brought you something to drink.
Oh, thank you.
There you
Thank you,
are.
Bucky. That's very kind of you.
Bucky.
Bucky's over there.
Okay.
Santa.
Now, I hear you're raising a lot of money these days for your Institute for Chemical Education.
Yes, indeed, I am.
So I brought you all this money.
Oh, thank you, thank you. Wow.
Okay, and just in case that's not enough, you can stretch it with this rubber band.
Thank you, Santa. That's very kind of you to stop by. I know you have.
Well, I have
You have
one
more?
more.
You
Now,
have
this
one?
one speaks for itself.
Uh-oh. I think I might use that too,
There
Santa.
you are. Okay,
Thank you
have
very
a Merry
much.
Christmas.
Same to you, and I want to thank you for stopping by. I know you have a busy schedule. Can you stick around
Oh, I
for
think
the
I
rest of
could.
this
I guess
program?
I'm ahead of things this year.
Well, that's good. I know Bucky would like to sit next to you.
Oh,
I've
that
saved
would
a
be
seat for
great.
you,
That
so-
would be great.
Okay. Now they seem to be getting along fairly well. One of the presents that I got is this can of soda, and I want to do an experiment with this. You know, beverages such as this one are carbonated. They have a lot of carbon dioxide in them, just like the carbon dioxide that we have released with Laura's help in this experiment. So what we're going to do is move over here, and you forgot something, Santa. Forgot something. Let me pass it on to you.
Yeah.
You
I
need
need
that.
that.
Yeah, right. Okay, let's take this baby bottle and take some of this liquid that's in here. You heard the can when it opened, that you heard a noise, right? That told us that something was happening. Let's stopper this and see what happens if, let's see, make sure this is sealed right. Small baby bottle with some carbonated beverage in it, and look what's happening to the... Now, I want you to know that this piece of rubber, I have another piece of rubber over here, just exactly the same as that one, is very strong and cannot be blown if you try to exhale into it. So I'll try. Watch this. And so that tells you something, tells us all something about the amount of carbon dioxide that's dissolved in this can of soda. Now it's, so you see that there is a lot of carbon dioxide that is in carbonated beverages. And we better release this pressure a little bit before this bursts, right? Let's see. You want it to burst? Okay, well, all right, all right. Okay, so we'll let that go for a while now and see what happens as we look at other properties of carbon dioxide. Now, carbon dioxide, we all know, is a gas. It also happens to be a substance that exists in a solid form, and it exists in the form of dry ice. And I have some dry ice. Let me just reach over and get some dry ice from over here. You know what? I just noticed that we have these beakers sitting around. We haven't done too much with them. Maybe Fred, we can call Fred again, and Fred can do a salute to Santa Claus. Fred, can you do that?
Oh, sure. I'll take it right out in front of Santa Claus so he
Okay.
can hear it real well. Okay. What kind of songs would you like to hear, Santa Claus?
Christmas carols.
Christmas carols.
Well, thank you, Fred. The experiment we want to do deals with solid carbon dioxide. We call that dry ice. And dry ice is very, very cold. Its temperature is minus 78 degrees Celsius. That's why I'm wearing the gloves to protect my hand from the cold. Now, dry ice is a substance that sublimes. It undergoes a process called sublimation. That means it changes from the solid state to the gaseous phase directly, without becoming a liquid. Well, I said it is carbon dioxide, solid carbon dioxide. And we want to do a couple of experiments with it with the acid-base indicators that Fred has brought out here. So I'll try to drop some chunks of dry ice into these different beakers. You see that the carbon dioxide bubbles off, and we see some moisture condensing near the top. And as we add some more, we might see if there are some chemical changes that are taking place. You see that some of the colors are changing already, telling us that a chemical reaction has taken place. And this is a mixture of different mixtures of acid-base indicators. And we now have evidence that carbon dioxide itself is a substance that behaves as an acid in water, because it causes different changes in these different indicators that we have placed in those beakers. So let's let that bubble for a while and move on and do a couple of other experiments with the dry ice. Let's take a look at this piece of rubber here. Boy, that's really very, very tight. It's about to explode. We don't want that to happen. So I'll just release it. I'll try to release it. Okay, so that's... What, you want explosions? We're going to have explosions. Just be patient. We're going to have real explosions, nothing like that. Okay? Where was I here? I was talking about dry ice, and I want to do an experiment involving dry ice and also a different substance, which is lime water. Now, lime water is a solution of calcium hydroxide. I'm going to take these 3 Pilsners and put some calcium hydroxide solution. That's lime water. All right, put that like so. And what we're going to do is try to see if I can get some volunteers to help me do this experiment. We're always trying to do some experiments all together. And so, you want to come out and help me? Come on out. Come on, come on. Come on. How about you? You come on and help me too. Come on. Yeah, you. Okay? What I'd like you to do is to hold this Pilsner, like so. Stand where I'm standing. Okay? What's your name?
Laurie.
Laurie? Another Laurie, okay. What's your name? Kevin. Kevin, you hold this like so from the bottom. Just like she's holding it from the bottom. I'm going to give each one of you a straw. You can let go of that. Yeah, right. I hold it like that, right? You come and stand right next to her, all right? That's good, all right? So I'm going to give you a straw. Here's a straw for you. And here's a straw for you. And when I count to 3, what I'd like you to do is exhale into the liquid. Don't drink the stuff now, okay? Don't drink it. So you understand what we're going to do? You blow very gently into it, and we'll watch and see what happens. So you ready? Okay, put the straw in there. 1, 2, 3. Very gently now. I don't want you to hyperventilate, then you'll pass out. So yeah, that's good. The rest of us are trying to watch and see if anything is happening. We look for different changes that may take place. Do you see any changes? Yeah, what kind of changes do you see? It's turning cloudy. You're right. That's what's happening. Okay, let's stop now. You feel okay, both of you? All right? All right. Thank you very much. Give them a hand for helping me, please. Now what they've done is shown by this experiment that what they exhaled contains carbon dioxide. Because carbon dioxide reacts with lime water to form calcium carbonate, a substance which does not happen to be soluble in water. It does not dissolve in water, and that's what this cloudiness is. Now we can do the same experiment much faster. You see it, they have the third Pilsner over there. Take a chunk of dry ice, and we put the dry ice in, and you see that the bubbling takes place, and the cloudiness develops much more rapidly. That's because there is a higher concentration of carbon dioxide in the dry ice than there is in our lungs. And the liquid turns very cloudy, and we'll watch and see what happens if we let the reaction go further. That's what we look for when we do experiments, changes, to see if we have evidence for a chemical reaction of any type. Now this reaction that's taking place, it has taken place in all of these three Pilsners, is the formation of solid calcium carbonate, which is limestone. And those of you who have been to Blue Mounds, to the caves, have seen calcium carbonate form there. In fact, you've seen another reaction taking place there too, that's taking place in this middle Pilsner. What's happening to the liquid in the middle Pilsner? Is it remaining cloudy, or is it changing?
It's getting lighter.
It's getting lighter. That means that the insoluble material, limestone, is dissolving, forming another substance we call calcium bicarbonate, and that happens to be a soluble substance. Now calcium carbonate, you see it's quite clear right now. Calcium carbonate is a substance that is formed very readily, and in areas such as ours, in Madison, for example, we know that all our houses and all our homes have in them water softeners. We have water softeners because we want to remove the hard water, the so-called hard water, which is due to the presence of calcium ions and magnesium ions. And I have some samples now of what I'm going to show you right here. This is a flask that contains in it some hard water that has not been run through the softener. Now hard water, as I said, has in it calcium ions and magnesium ions. And what we want to do when we use a softener is to remove the calcium ions and the magnesium ions, because they form an insoluble substance with carbonate, as we've just seen before. So the way we do this is we take the hard water and we run it through the water softener. And I have an example of what is inside the water softener. What we want to do is run it through a substance which we call an ion exchange column. We want to exchange the calcium ions and the magnesium ions for a different set of ions, namely the sodium ions that happen to be soluble. Now why do we want to do this? We want to do this because the properties of hard water, I have another sample of hard water here. If I take some soap, for example, and add it to the hard water and try to, see, it doesn't froth very much. Took some liquid soap, it doesn't froth very much. But I have some soft water over here that has been run through the softener. I take some soap, add it in, and stopper this, and you see you get a lot of froth. And that's why we run the hard water through the softener. So that's what we're going to do now. Take some hard water, add it, open this, and what we're collecting down below is soft water that has the calcium ions and the magnesium ions removed. These are removed because they are exchanged on this ion exchange material, this resin. And every now and then, you know, we add sodium chloride, we add salt to the water softener. That's when we recharge this column. After it gets saturated with calcium ions and magnesium ions, we have to remove them. And what we remove them by is flushing the whole column with a solution that contains sodium chloride. That's why the salt is used. So let's stop now and see if this is indeed softened. Let's see, here's some soap. And I'll borrow this stop from here so I don't splash it all over the place. And you see the soft water behaves the same way as this sample did. And that's how the softener in our homes works in order to remove the hardness of water, namely the calcium ions and the magnesium ion. Now we've seen some examples of different behavior of carbon dioxide and solution of carbon dioxide. I want to show you one more property of carbon dioxide. We all know that carbon dioxide is a substance that's used in fire extinguishers, right? It's used to put out fires, and what we're going to try to do now is to show that that is indeed its property. So what we'll start working with is get a flame going. And what I'll do is take some, oops, this is the wrong hand. Take this one. I'm going to take some chunks of dry ice and put them in the bottom of this beaker. What happens to dry ice when we let it sit like so? It sublimes. It changes directly to a gas. And I'm going to take this piece of wood, light it up, and what do you think will happen to it if I put it down there? See, it goes out, telling us that carbon dioxide does not support the combustion of wood. Now, you know that carbon dioxide fire extinguishers are not used for all types of fires, only for certain types of fires. Supposing that you have a fire in the kitchen has a lot of metallic items in it. You don't want to use a fire extinguisher that has carbon dioxide in it because, well, let's see what happens if I take a piece of magnesium, which is a metal. I'm going to take a piece of magnesium, and I'm going to put this in the flame, and it starts, you see it's very bright. Don't look at it directly, but you can see it's quite bright. I put it inside here, and let's see what happens. And I have another piece of, I lost most of it. Now carbon dioxide, you see, supports the combustion of magnesium. So metals should not be, if you have a fire with a metal involved, you should not use a carbon dioxide fire extinguisher for that purpose. One more time, see? And it just burns out completely, and you should not use, as I said, a fire extinguisher that has carbon dioxide in it for putting out fires of that type. Now we've seen different examples of the chemistry of carbon dioxide. I want to show you one more, and this has to do with doing an experiment. And this experiment involves, again, an acid-base indicator. I'm going to see if I can get somebody to help me do this experiment. Gene, are you ready to help me? Okay, come on out and help. I have a pair of goggles for you here. Okay, and what we're going to do is carry out an experiment over here in these 3 flasks, and we're going to use some seltzer and some acetic acid and some indicator. What I'd like to ask you to do is to put 50 milliliters of acetic acid into this flask, and then 50 milliliters of the carbon dioxide that's dissolved in this bottle into each of these other 2 flasks, okay? That's good. Okay, so that's the carbonated water. Another 50 ml into the second one. That's good. We'll take this out of the way, and then we'll take this out of the way too, and put the acetic acid into this one. So we'll remember that the 2 flasks on our left have in them the soda water that's carbonated, and the flask on our right has in it, will have in it shortly, the acetic acid. So go ahead, Gene, and put that in there. Now, we've learned tonight that these substances are all acidic, so if we put an acid-base indicator in there, such as we have in this bottle, which is labeled bromethymol blue, why don't you put a few drops of indicator, like about 5 in each, okay? Okay. And then in this one, Okay, now what I'm going to do is show you how, whoops, I've got to get the right reagent. I'm going to take some sodium hydroxide out of this bottle. Take this and shake this up a little bit like so, so the indicator is dissolved completely. We're going to take some sodium hydroxide. We know sodium hydroxide is a strong base. It will react with the acid. What we want to see is how fast it will react. So we'll look for color changes. So are you ready? Okay, we'll do this. And you see there was a color change that took place. That's because the base has reacted with the acetic acid. Now, I'll do the same thing with the second flask. And you see there's a change there too, but this change has taken place at a certain rate. Now, carbon dioxide is involved, of course, in our lungs. As we exhale, the blood loses carbon dioxide. Clearly, the color change that's taking place in this flask is not very rapid. In fact, if we had to wait for this exchange of carbon dioxide between the blood and what we exhale, then that would be insufficient time for us to absorb oxygen, gaseous oxygen. So what is in the blood then that makes the reaction very fast is a catalyst. And this catalyst is called carbonic anhydrase. And we want to test the effect of this catalyst by simply drawing some blood. Are you ready to do that?
Not me.
Not you? Okay, how about if I do it? All right?
That's fine.
That'll be fine with you? Okay, well, I've arranged for somebody who's had a lot of experience in drawing blood, and that's somebody with training in medical technology. I want to ask him to come out and do it right now. So come on out, okay? Gene, you just watch and see what happens now to this reaction. And would be okay with you if he drew my blood, wouldn't it?
Fine.
Fine? Yeah. Okay. So what we have is now we're going to try to get some of the catalyst, carbonic anhydrase, into this sample to see if the rate of the reaction is different than it was without the catalyst. Remember, these two flasks had the dissolved carbon dioxide in them from the soda water, okay?
Okay,
You sure you've had enough training doing this?
sure.
Boy, that feels cold. What are you rubbing on there?
That's 70% alcohol.
Alcohol. So then alcohol is evaporating, and evaporation is a cooling process, so that's why it feels cold, right? Bucky, you knew that all along, didn't you? Right? Okay, I'm ready. And here we have blood. Okay. What is this now? Capillary to okay. Keep squeezing my finger. Did I give you a good grade or what? Okay. Up to the mark, that's enough. You want to give me something to put on? Yeah. Thank you. Okay. A Band-Aid too. All right, great. I'll use that. All right.
Okay.
Now what I'd like you to do is to place the blood sample into this. You want to use this to blow it?
Sure.
Will that work? Yeah, that should work. Not big enough?
I'm not sure.
How about the syringe? Will the syringe work?
Might not be big enough. Let's try.
Okay, so we have some blood, and that has the catalyst carbonic anhydrase in it. And we'll mix this up, and now we'll see what happens when we add the sodium hydroxide to see if the reaction takes place at a different rate than it did in this flask. So here we go. See what happens. You see it was quite fast compared to the way it was before, showing the presence of this carbonic anhydrase catalyst. So thank you very much for coming to help me, and Gene, thank you for helping me. Okay, now we're going to do one more experiment with carbon dioxide. Then we're going to move to a different chemical that's related to carbon dioxide. What I have here is just an empty trough. I've got some water that's been boiling. I'm going to add the water in here. And the experiment we're going to do is a very simple one. I'm going to find the glove, and we're going to add some carbon dioxide, solid carbon dioxide. And you see what happens when you add carbon dioxide like so. it looks as if we have smoke. And that's how they make smoke in the movies. It's one way of making smoke in the movies. That's because the moisture is condensing, the moisture in the air, and the moisture from the hot water is condensing around the carbon dioxide that's escaping, and we have this very special effect, which is due, again, as I said, to the reaction between the carbon dioxide that's escaping and the moisture that's in the vicinity. Okay, so let's move on and to a different kind of chemical. We've talked about the oxide of carbon, namely carbon dioxide. Now we want to show you some fancy experiments with a related oxide, that of silicon dioxide. Now we're going to move over here, and you've all seen silicon dioxide. It's no big deal. Silicon dioxide is nothing but sand. Sand is silicon dioxide. I have a sample of sand over here. You've all played with it one time or another in a sandbox, where have you. This is silicon dioxide. The formula for it is SiO2, silicon dioxide, but it occurs in nature in a variety of forms. And through the cooperation of the UW Museum of Geology, I've been able to obtain some samples of different minerals that have in them silicon dioxide. Here, for example, is black mica. You can see that the very, very nice pattern that it has in it. Here's another sample of a mineral with a very colorful composition. All of these different samples contain silicon in the form of silicon dioxide. This big chunk that you see over here is quartz. Now, quartz is a special form of glass, and we want to show you now some experiments with glass. And to do that, we're calling on the departmental glass blower, Charlie Ameling. So, Charlie, come on out here, and let's have some experiments with. Now, Charlie, what do you have here? You have a tank that has in it what? Oxygen?
I have oxygen, and I got.
You want some? Okay, I'll come around and do that. Okay, so you need a source of gas. All right. Got it? All right, now what are you going to do? You're going to light up the burner.
First, I'm going to light up the natural gas.
Okay.
There we go. And this is the same kind of torch that you might see in a welding shop, but I use it for glass blowing.
So what you have is oxygen. Oh, is it pinched someplace? Maybe I didn't open it up far enough. Let's do it again. Is that better?
Yeah, there we go.
Okay.
Thank you.
So what are you going to do now?
Okay, these glasses that I wear are tinted. They're called didinium glasses, and they'll filter out part of the glare from the glass by heat.
All right.
I'm going to show you 3 different types of glasses.
What's the first type?
Okay, soft glass. Second type will be quartz. Third type will be pyrex. They all look the same when they're not heated. Okay, first I'm going to go with the soft glass. And soft glass is the same glass that's used in your windows. And when I'm heating this, I'm going to warm it up kind of slow because it'll shatter. I heat it up really fast. It has a very high thermal expansion. Okay, you should be seeing the glare now. And with these glasses on, it filters out about 90% of the glare. Now what I'm going to do is it's just heated up enough to make a round bottom. Take it out of the flame. Just made a little round bottom. I'm going to stick it in the glass. And as you can see, it just shattered.
Yeah.
Just from the thermal expansion. Okay, now I'm going to take a piece of quartz, which is about 99% silica. The soft glass was about 72% silica. Now you can see this takes a lot hotter flame to melt it. And the glare will be a white type glare. So this is actually white hot, which is about 1700 degrees centigrade. Okay, I'm going to make a round bottom again with the quartz glass.
Boy, that's very bright.
And I'm going to quench it in the water. And you see nothing happen to the glass.
Didn't break. So
Okay.
this has a different thermal expansion
Okay, this has,
property than the other
comparing the
glass.
two, this has a thermal expansion of 1, this is 16.
16,
Okay?
okay. All right.
And the glass that I use mostly in glass blowing here in the chemistry department is Pyrex. And this would be right in between the two. Has a thermal expansion of maybe, if one was 16, soft glass was 16, and that was, quartz was 1, this would be about 6. So it has both properties. And it's just in between. Now I'm just going to heat up the end of this here like I did the soft glass and make a big round bottom this time. I'm actually gathering the glass up on the end here. And I just give it a little blow harder here.
Oh, wow.
Okay, that's the Pyrex.
Okay.
Okay, this is Pyrex too. I started a little earlier here. And I want to show you a little bit more of what I do at work here. Again, I'm heating up the glass. And you can see a point out on the one end of the glass here. I'm going to pull another point here on the other end. And you can see you have to rotate the glass continually. Because it is a poor conductor of heat. If you heat one side, only one side will get hot. And just take it, and as long as you have control of the glass, you can do anything you want to it. There's one bad thing about glass, it looks cool when it's still hot. I'm just going to cool this off a little bit here. Okay. Now what I'm going to do is just try to gather the glass up here and blow a little ball. So again, I'm rotating the glass the whole time I'm heating it.
Glass is actually a liquid that's an amorphous substance, right? That's why it flows like that. It flows very slowly. When you heat it, it becomes soft. Doesn't really melt.
That's right, there's no melting point for glass, just a softening point. And the hotter you get it, the more less viscous it gets. So if I just held it in the flame, it would actually heat up enough and it would drop off. So I continually rotate it to heat it evenly and try to get it to the right temperature. So you can see the Pyrex really lends itself to glass blowing, especially in laboratory glassware. I just made a round ball this time. I didn't get too excited. Okay, I'm taking a piece of blue glass here, and this is Pyrex glass that I put some cobalt oxide in, and it actually turned it blue. There's different oxides, makes different colors. I'm just going to add some color to this. Just open the drawer here.
Reaching in for some tools.
Yeah, there we go.
All right. Okay.
All right. Now I'm just going to heat up the little blue tip on the end here. And you can do anything you want with glass. If you blow on it, it comes out, and if you push on it, it pushes in. So once you have control of the glass, you can make any shape you want. I just put a little color on there so you can see the pieces going in a little bit.
I'm beginning to see what you're making here.
Just a little Christmas ball.
Yeah, it looks very nice, and Santa Claus, I think, would appreciate keeping this. Would you mind giving it to Santa when you get done?
As soon as it cools off.
We have to wait for it to cool off. Oh, okay, okay. Well, that's a very interesting demonstration, Charlie. Thank you very much for coming out to help out with us. Thank you. Okay, I'll get the gas out the way here now. All right, let's move on to do some other experiments with a different set of chemicals. These chemicals are ones that we're going to make right here. Now, in making these chemicals, of course, making any chemicals, you've got to mix reagents together for a reaction to take place. I'm going to use these rubber gloves to protect my hand from possible spillage, because some chemicals are not very friendly to the skin. We always have to be obeying safety regulations in doing experiments. You notice that Charlie was very careful in handling the glass, and you notice, of course, he was wearing eye protection. So was everyone else that has helped tonight. So we'll take two different chemicals, and we'll mix them together into this beaker, and we'll see if anything happens. So here we go. We mix those two together. We have two viscous kind of liquids, and the next thing that we do is take this glass rod and mix them up together. We mixed approximately about 40 milliliters of each viscous liquid. We know that chemicals don't react with each other unless they're mixed very, very thoroughly. Some reactions are fast, some reactions are slow. It's what we do in science, try to understand why some reactions are fast, why some reactions are slow. Try to get some insight into the different forces that hold chemical together, the different energy that's released when chemicals are mixed together. And we'll mix those two some more, and we'll see what happens if I stop mixing anything, okay? So we'll wait and see if anything develops as we move on to do a different experiment. This experiment I'll do in this beaker right next to this one, and I will take some liquid, add this liquid in there, and then try to take some water. I had some water around here someplace. I'll just use what was in this, okay, which was the soda, and then I'm going to add some acetic acid. We add some acetic acid, and we see that this liquid that I've added before has coagulated. It has formed a rubbery material. This is latex rubber. And what we'll do is try to fish this out. Try to fish it out like so, and dry it out. Looks kind of messy. Okay, get all the water out. Now, meanwhile, you're watching what's happening in the beaker that I put the reagents in a while ago. What is happening? You see what's happening? Okay, now what's happening is that we're forming polyurethane foam in that beaker, which is a form of a polymer, as is this one. What I have in my hand right now is latex rubber. You've all had many experiences with using rubber bands and using different kinds of properties of material that involve rubber, gloves, for example. And what I want to show you is one property right now which involves using this wheel that I have. Now, before we do that, let's take a look at the polyurethane foam. You see it's rising very, very rapidly. Now, this bicycle wheel, we've had all the spokes removed from it, and we've replaced them with pieces of rubber that have been stretched. Now, one of the properties of rubber, of course, here's a piece of rubber, is that we can stretch it. Now, one thing that happens when we stretch rubber, well, we can do a lot of experiments with rubber when we stretch it. And I want to ask somebody to come and help me with this. Tricia, you want to come out and help? Come on out here, okay? I'd like, come on out. Now, what year of school are you in?
I'm a senior.
You're a senior in high school? Okay, I want to give you this rubber band, and what I'd like you to do is to stretch it. Okay? What I'd like you to do is, play around with it like so, and then I would like you to bring it next to your forehead, and then stretch it and put it quickly on your forehead, and tell me what you feel. What do you feel?
It's warm.
Feels warm? Okay, let's do it again. Stretch it, put it on your forehead, keep it stretched. Now put it up front, like so. Now cool it quickly and put it on your forehead. What does it feel?
Cool.
Feels cool. So when we stretch the rubber, then it gets hot, right? And so what we're going to do now is heat this with this wheel that has the rubber spokes in it with this infrared lamp, and see what happens. You see now what's happening?
It's contracting.
The rubber is contracting, and because of the contraction, then the wheel, which is very well balanced, begins to move. So this is one important property of rubber that we need to know about and we need to be aware of. Now I'm going to do one more experiment for you with this balloon. Okay? I'm going to take this balloon that Santa Claus gave me. Why don't you put your safety goggles on, Tricia? Okay, that'll be everybody. Thank you. Okay, we're going to take this balloon, blow it up. No big deal, right? Okay, just an ordinary balloon, right? And you see that small vial at the end of the lecture table? Can you bring that over here? That's, yeah, that yellow one. No, this one over here. This small bottle. Okay? Okay? What I'd like you to do is to hold this balloon for me like so. You just hold it? Both hands. Give me the other. Give me this. This is just a little bit of oil that I'm going to put on this very sharp needle that Santa Claus brought. Okay? And what I'm going to try to do is put this needle through the balloon without having it pop. You think I can do that? Probably, but you're not sure, right? Let's find out. Let's find out. Put this needle in like so. Okay, there's the needle. There goes the needle. And you see, have you ever seen a knitting needle like this drawn through this before? Okay, we pull the needle out, we get the balloon, and it pops. Okay? Tricia, thank you very much for helping out with this. Thank you. I want to thank you all for coming tonight. I want to thank all my special guests for being here tonight. I hope that you have gotten a flavor of how fun chemistry can be. Thank you very much, and Merry Christmas to everyone.
Wow.